So in this example, we're going to look at Coulomb's law and an equilibrium point. So in my diagram, I have a red charge and a yellow charge. The red charge is -1 Coulomb. The yellow charge is plus 1.2 Coulombs. And they're at the points 0, 0, and 1, 0, respectively. So my question is, where could I put a third point charge Q equals plus 2 Coulombs such that it feels no electric force? So before we jump into the math of this problem, let's look at it qualitatively. So suppose I put my charge Q somewhere above the 2 point charges on the x-axis. Well, the vertical components of the force on Q may or may not cancel. We don't know. But there will always be some horizontal component of force. Just sum up the two forces from those 2 point charges on the x-axis. Same thing, if I put the point charge Q below, it will always feel some force. So it can't be in equilibrium above or below. If I put it in between the 2 point charges, it will also feel a force. Why? The yellow and the red are going to work together to pull that blue charge to the left. If I put it to the right of the yellow charge, we notice that the yellow charge is bigger than the red charge, and it is closer to the blue charge than the red charge is. So it will actually cause a greater force on the blue charge Q than the red force can. And so the blue charge Q will drift to the right. But if I put the blue charge Q to the left of the 2 red and yellow charges, there is a chance that it might find an equilibrium spot. Why? The red charge is smaller in magnitude than the yellow charge, but it is closer to the blue charge than the yellow charge. So I'm going to call the distance between the blue charge and the red charge x, and I'm going to call the distance between the red charge and the yellow charge 1 meter. And now, after all of that, let's go through the math here. So first I'll write out Coulomb's law. Force is K, Q, Q divided by R squared, R hat. I know that the magnitude of the force between the red charge and Q has to equal the magnitude of the force between the yellow charge and Q. I can write those two out. K, Q red, Q divided by x squared equals K, Q yellow, Q divided by 1 plus x squared. I'm getting the 1 plus x as the distance between blue and yellow. And remember, x is a positive number. I can cancel out the K and the Q, which leaves me just the ratio of the red charge to x squared equals the yellow charge to 1 plus x squared. And I can do a bit of rearranging. And now I see I can just plug in some numbers and finish up the problem. So I'll plug in the values for the red and yellow charges. Notice I plug in +1 for the red charge, because remember, I'm only dealing with magnitudes here. And I can do a little bit of simplification, and I get x is equal to 10.5 meters, right? Now people often ask me, how do I know it's 10.5 meters, right? This is a quadratic equation. Don't you get 2 solutions? The answer is yes, you definitely do get 2 solutions. In my case, I get a positive and a negative solution. But remember, I defined x as a positive number. It's the magnitude of the distance between the blue charge Q and the red point charge at the origin. So the negative answer is unphysical, right? So in conclusion, remember, the actual charge on Q does not matter in this problem. You'll notice that we canceled Q early on, and so it doesn't matter if it's positive or negative, big or small. Second thing is, be careful with directions and negative signs. Most of the time when people come to me with questions or mistakes on problems of this caliber, I say, make sure you define your convention, define your axes, draw a picture, and stay consistent throughout the entire thing. And finally, give this problem a shot with the red and yellow charges switched. Maybe give it, maybe move them around on the axis, or try it with a different point charge Q.